All right, it looks like the recording's going, so I'll get started. This is just going to be a video for the Spirogravitator derivation. Um, it's kind of a long one, so make sure to follow through and understand each part. There's a lot you can learn from this derivation, and I will say it's probably one of the trickier derivations that we'll go through in this entire course. And you'll kind of see why the spirogravitator is a really interesting circuit. But the purpose of this video is, yeah, for you to follow along, and you'll need this entire derivation in your lab notebook. So make sure you just kind of write along with me as you write this. And after we get through the full derivation, I'll also do a quick introduction to the MATLAB code. And I'd like you to also watch through with that so you can see some of my coding practices and pick up how I solve those problems. But without further ado, let's just get started on this derivation. So I'll share my screen. Excuse me. Okay, so this is the circuit that we're looking at. Let's make sure that this is the right screen I am sharing real quick, because I don't want to film this whole thing and have to do it again. Yeah, I think that's working. Okay, sweet. So, oops. Where was I? There we go. And also, I'm not using the best writing surface, so please bear with me as we get through this derivation. But it asks us to find or derive V1 of S and V naught of S in this circuit. And for the most part, we just want to use the Laplacian transform method. And I think you've already discussed this in class, so I'll kind of go through this pretty fast. But the first thing that I want to acknowledge is a capacitor's Laplace transform. And so in the Laplace domain, the capacitor's transformed into this sort of system. We have an impedance Z sub C is equal to 1 over SC. And we have a voltage source, VC, so the voltage across the capacitor at time t equals 0 minus. So whatever the voltage, whatever the capacitor was charged up to before the switch. And then that's all over S. So this term VC over S is how we actually model a constant voltage in the frequency domain or in the Laplace domain. So what this is saying here is whatever constant voltage the capacitor was charged up to before the switch. Okay, so before we move on, let's continue to look at this capacitor. So we've separated this capacitor into C1, and I'm going to just label this C2. Okay, we are told that the time input of the circuit is this 2 volts peak to peak square wave, where the negative polarity is -1 and the positive polarity is 1. Or I should say the low is -1 and the high is +1. And so we know that it switches at t equals 0 right here. And again, I apologize for my handwriting, but yeah, so the capacitor was charged up to -1 volts. And we are also told that the period in the lab handout, we're told that this period, capital T, is large enough that capacitors can charge up fully each time and then some. So we know the capacitors were charged to -1 volt, and we've separated the capacitors into 2 different capacitors of equal value. So that is to say that C1 equals C2. And we also know that VC at t equals 0 minus is equal to -1. So when we do our Laplace transform, we can now go ahead and do that fully. We're going to have our voltage source V of S, because we're in the frequency domain now. That's just grounded. Then we have our resistor R1. We have our inductor, or I'm going to model it as an impedance because we're in the frequency domain. So that's S times L. That's Z sub L right there. And then we have our first voltage source from our first capacitor transform. Then we have our capacitor 1 over SC1. We have our node V1. We have our second voltage source plus to minus, and then we have our second capacitor 1 over SC2. And then we have our resistor R2. We have our negative terminal of our op amp. So that's plus minus. And then we have our feedback loop with the R3 term right there. Ooh, maybe I can do a little better on writing that. There we go. And then this is the node V out. And so those are the two voltages we're looking for. It's also, let's figure out what these capacitors voltages are. We said that the whole capacitor was charged up to -1 volt, and we've separated it in half. So across each of these, we see -1 over S, 1/2 S, because I separated 1 volt into 2, so there's a ½ volt drop across both of these. 1 over 2S, -1 over 2S. Okay, so now we know from the golden op amp rules that V sub n, which is, I'll write it right here, this is V sub n. V sub n is equal to Vp, which equals 0. And this is sort of the power of using op amps in general, but also in the frequency domain, we can do some really cool stuff. So I see that if this is ground right at this V sub n terminal right here, then I can write some real quick equations. I'd also like to acknowledge the other op amp rule that the input current to the op amp is 0. So maybe I'll switch over to blue. That tells us that we have one current that goes through this whole circuit in this branch and then up through the feedback loop. And that current I will label as I of S. Okay. And maybe sometimes, by the way, I will just write I for simplicity. Okay. So let's come up with some KVL equations. We could use node analysis. I'm going to do a KVL here because it's simple for me. So let's do our first KVL. I'm going to try this gray pen out. We'll see how it goes. But I'm going to start here. Ooh. Yeah, I would like to switch colors for my KVL. So I'll start here at V1 and I'll go all the way down to V sub n. And so that's V1 minus, and here I drop minus -1 over 2S. Okay, minus, I'm also going to drop the voltage of the current times the total impedance that the current goes through. And here we go through the impedance of 1 over SC2 plus R2. So I'll write that out just as it is, 1 over SC2 plus R2. And so this is, I want to take a quick pause here and explain my perspective. What I'm doing here, this is just Ohm's law, right? I have a current I times a resistance Z total here. That's the total current, or the total impedance the current goes through. And it's important to acknowledge this for a few reasons, but I'm just going to leave it real short and simple and say that the units of Z, so the units of impedance, sometimes I'll use brackets to denote the units. The units of impedance are just ohms. And so this is a powerful perspective to have when you're doing Laplace transforms, because it really forces you to acknowledge that we can use all of our previous circuit knowledge. Everything we learned from circuits 1 and 2, we can apply here. And I want you to keep that in mind, because while this problem appears really scary in the time domain because of the inductors and the capacitors, in the frequency domain, it's just like anything else you've seen. It's just, just current dividers and current loops. So it's really nothing new if you can keep that mindset going on. So we can therefore, well, real quick, I'm also going to end this KVL. I'm going to say that that's equal to 0 because when we drop that voltage and that voltage, that puts us at the terminal V sub n. Maybe I'll just write it's equal to V sub n, which is equal to 0. Okay, so here we have an equation for V1, and we'll actually solve for it in a moment. But yeah, we can move these two terms over to the right-hand side and have our equation for V1. Now let's do another equation. I'm going to start in purple still. I'm going to start at terminal V sub n and go up and over to V out. Okay, so what is that equation? I'm going to give you a moment to think about it. So we want to start at 0 volts. That's V sub n. And we're going to drop I of S, the current, times the resistance, R3. And that will be equal to V out. Okay, there's our second equation. Real easy. Just Ohm's law, really. So we have these two equations for the terms we're looking for, V out and V1, but we don't know what I of S is. So we can find it by coming up with a third equation, because we have 2 equations and 3 unknowns. So how can we find I of S? Well, let's start at V of S here, and we'll drop all the way down to 0 volts. Okay, so V of S. And then there's a few ways we conceptualize this. We could go through each component one at a time, but I'm going to show you a really speedy way to do this. I'm going to drop the total voltage in this branch. The total voltage I'll drop, as far as strictly voltage units, are minus 1 over S, 1/2, or sorry, 1 over 2S, and then again minus another negative 1 over 2, or sorry, minus a negative 1 over 2S. And so that's minus 1 over 2S, minus 1 over 2S. And so just to kind of clean stuff up as we go along, I can see that those will both become positive. And if we have 1/2 plus 1/2, that's just 1. So I'll just express it like that. So we're going to have plus 1 over S. So that handles all the voltage drops. Now we have all these impedances and this current, so I can also just say we'll also drop the voltage of I of S times the total impedance. And I can just add that up here. It's going to be S of L plus 1 over SC1 plus 1 over SC2 plus R. And this R value, I'm just going to write it like that for simplicity, but R equals R1 plus R2. So that's my new equation here. And let's see where this can get us. Okay. So this is all equal to Vn. That's where I stopped my KVL, and that's equal to 0 volts. So now let's solve for I of S, and I can quickly write out that I of S is going to be equal to this V of S plus 1 over S divided by my denominator, which is S of L plus 1 over SC1 plus 1 over SC2. And maybe I could just quickly clean this up and express this as 2 over SC1 because we acknowledged earlier that C1 and C2 are equal. So 2 over SC, I'll say 2 over, yeah, 2 over SC1 is great, plus my R term. So that's my denominator. And this expression is my current. Okay. Let's make our lives easy by finding out what the form is what the form of this equation is in the Laplace domain that would easily allow us to transfer to the time domain. And that's kind of a mouthful, so maybe I should just quickly open up the Laplace transform pairs so that we can see what those are visually. Just a moment, sorry. I'm just opening up the lab 2 Laplace transform pairs table. You probably should too, but you can see it on my screen in just a moment. And here it is. So what I'm saying is, if you read the lab handout, we know that we are trying to get to this sort of scenario. We know that our time-dependent equation is going to model one of these 2 equations. And so our current should look something like this form. And I can see that because I know my V out equation is my current times R3. So the form of the Laplace frequency dependent equation, it should be something like this, one of these 2. So let's just a moment. Let's go through and figure out what that is. Okay, so we can factor this equation and manipulate it to get it in that form. That's kind of where I'm going. So we know that this is equal to, well, let's analyze this V of S term real quick. V of S for time t equals 0 plus is going to be V at t equals 0 plus over S. And remember, it's a square wave, so it's positive 1 volts. So this numerator can be expressed as positive 1 over S plus 1 over S divided by my denominator. Here, I'm going to add all these components up so they have the same denominator. This is kind of the general flow for these sorts of problems. So when I do that, I'm going to distribute this SC1 denominator through all of these. So I'll be left with S squared LC1 plus 2 plus R times SC1. And that's all divided by SC1. Okay. So now there's this interesting thing that happens. I'm going to express my numerator as 2 over S multiplied by my denominator. And I can see that the denominator of the denominator is SC1, which is the numerator. That is to say that 1 over A is just equal to A. That's just some basic algebra that I know I had forgotten by the time I'd taken this course. So just a little refresher there. But so that SC1 term will be my new numerator, and then I have my denominator. Well, the next step with this factorization is to isolate the leading term of S. And that is to say that the coefficient on S squared, which is my leading term, my highest power, the coefficient of that term is LC1. So I want to factor that out of all my components. So I have LC1 times S squared plus R, and I factored out the C1, so that will go away. I'll have R over L, because there was no L term in that. Plus, let me slide this screen over a bit. plus 2 over LC1. So that's my whole denominator. And now that I factored those terms out, I can see that quite happily these C1 terms cancel and my S terms cancel. Okay, now that's really convenient. So let's continue on with our I of S equation. So now I have 2 over L times 1 over S squared plus R over L times S plus 2. Okay, now this next step, it's scary for everyone. Nobody likes to do this, but fortunately there's an easy tried and true method of completing the square. And there's a lot of ways to do this. You can do it visually. You can follow a sort of limerick, like a song to help you remember this. But the way that I like to do this is just use the equation. That really speeds stuff up. Okay, so completing the square, we know that ax squared plus bx plus c equals 0. So we can set any quadratic equal to 0, and we can factor it like this. It's a times x plus b over 2a all squared plus c minus b squared over 4a. So let's apply this equation to our denominator of I of S. So I have 2 over L times, here I'm going to have 1 over, my A term is 1, so I'm going to have x, or sorry, not x. In this case, I'm using S plus my B term is R over L here. So that's R over 2L. And then A is 1 again. So that's all squared. Plus C here. Oh, I forgot to carry the 2 over LC. So C is 2 over LC1 minus B squared would be R squared over L squared. So then this term is R squared over 4L squared. And that's my new denominator. Okay, very nice. Now let's go one step further to just say, if we want to express it in this term, we can express it in this one. So I can do that by expressing this as S plus alpha squared plus beta squared, where beta is just this term. Okay, now, if you haven't seen these alpha and beta terms, this is a good place to write them in, and I'll do it in red so it's a little easier to see. But alpha equals R over 2L for a series series RLC, which is what we're dealing with. And we also know that alpha squared plus beta squared equals omega squared, which is 1 over LC. That is to say that omega is the square root of 1 over LC. Okay, so these terms are really nice to have. Interestingly, they show up in almost every type of oscillating system. I'm not sure what their names are, but alpha and beta are good equations to have in our pocket, because now we can express I of S like this. Okay. So going back to our equation for V out, or V naught, it's negative I of S times R3. So we can write this out. V naught of S equals negative 2 over L times R3 times 1 over S plus alpha all squared plus beta squared. And so V naught of S is nearly finished because I can see, let me do this quick screenshot. And drop this over here. I can see that my equation follows that term perfectly, or this form perfectly. So I'll just write, therefore, that's what this arrow means, by the way, in math, just in general. It's a nice one in electrical engineering, but therefore, V naught of t is just going to be equal to, well, I can see that in this form, beta squared is omega squared. But I don't have an omega term in my numerator. What I have in my numerator, I have -2 R3 over L in my equation, and I need that to be equal to beta omega, or B omega. So I can see that B is equal to this term divided by omega. And so what that means is that what I really have for my time-dependent equation, I have my B term, which is -2 R3 over L omega. I'll just express it like that. Well, in this case, sorry, I hope this isn't confusing. In this case, I've labeled omega as being beta. So beta. So that handles this part of the equation. Now I have e to the negative alpha t, because a is alpha in our case. And I have the sine of omega t. And here, remember, our omegas are actually betas. All right. So that gets us V naught of t. We're done with that part of the problem. Strangely enough, we're only about halfway through this derivation because V1 of S is kind of a doozy. So let's work through it. So V1 of S, remember, that was equal to our current I of S multiplied by 1 over S C1 plus R2 minus 1 over 2S. Okay, let me just verify that that's what we had. Yeah, I'll shift. This would be a plus, and then I'd shift it over, so it'd be a minus, and that should be a plus I of S. So yeah, I've got this correct here. Okay, so we know, again, excuse me, we know that 1 over 2S term is just a constant in the time domain. But this term, this is going to be the thing that gives us trouble. So let's break it out. I'm going to call this term f of s. And it's going to be equal to, we have 2 over L times 1 over S plus, sorry, I'm not going to call that f of s yet. So I'm going to continue writing out this left term. So that's S plus alpha squared plus beta squared times 1 over SC1 plus 2 over L times R2 times the denominator, which was S plus alpha squared plus beta squared. So there's our denominator. And what I want to point out here is that this entire left term, this was just C V naught of S. It's the same thing, but instead of R3, we just have R2 here. So this one we've already done, essentially, and I'm not going to continue with that part of the derivation. But I am going to focus on this left term. This is the one that's kind of a pain. And this is the one that I want to call f of s. And I'll show you why. Because we pull out our Laplace transform pair, and I can see that I have this omega over s plus a squared plus omega squared times b. That perfectly models our current part. However, this 1 over sc one term throws a wrench in stuff because we don't have anything like that in the Laplace transform pair. And unfortunately, it's not a linear function or a linear operation, so we can't just multiply it by like 1 over s. We can't do that, unfortunately. So we have to go with a more complicated approach of partial fraction decomposition. And normally, I'll call that partial fraction decomposition, PFD, not personal flotation device, but PFDs are usually pretty easy to work with. However, in this case with the spirogravitator, it is really difficult to work through the partial fraction decomposition, as I'm sure you'll see in just a moment. But just keep in mind that this is probably the hardest partial fractions problem that you'll see this whole course. I honestly think that the homework will be quite a bit easier. So f of s is equal to all of that stuff. So I'll just write it out. 2 over L times 1 over SC1 times. Here we have 1 over S plus alpha squared plus beta squared. Okay, so I can express this through partial fraction decomposition as A over S, because I see I have a 1 over S term here, plus B at, I'm going to say it's ds plus E divided by my denominator, S plus alpha squared plus beta squared. Okay, so looking at this, if you're unsure as to why I have this ds plus E term, it's because we have an s squared in the denominator here. So we're actually going to end up with two different terms for that fraction, that partial fraction. So that's how I chose to express that. Now, if you haven't seen this technique for partial fraction decomposition, it's a little confusing, but I'm going to show you how to quickly eliminate and solve for a single variable. And this really works well for scenarios where we have like A over S plus B over S plus E plus C over S minus E, stuff like this, where we have like really, it's called a distinct root. Where we have distinct roots, this term works especially well. And unfortunately, it doesn't work for the spirogravitator, but we can find our A term. So yeah, I'll show you what we're going to do. We're going to say that f of s times s, so that's the denominator on A here, f of s times s evaluated at s equals 0. What will that be equal to? I know it's going to be equal to A over S times S plus ds plus E all times S divided by my denominator, S plus alpha squared plus beta squared. And that's equal to A. Let's see why. So if I go ahead and cancel some stuff out, I see that these s's cancel, so that's A right there. And here I have a bunch of stuff times 0. So that gets rid of that whole thing. So f of s times s divided by, or evaluated at s equals 0 equals A. That's super convenient. And this sort of approach, like I said, works well for distinct roots. It's not going to work for this ds plus E term, but we'll get through it all in just a moment. So that's the right-hand side of my equation. All of this stuff was equal to A. But on the left side, I'm going to have 2 over LC1 times S over S times 1 over S plus alpha squared plus beta squared. Okay. One sec. Let's pull out the red marker. These cancel, and S goes to 0. So what I'm left with here, I have the A equals 2 over LC1 times 1 over alpha squared plus beta squared, which is equal to, that's 1 over omega, and omega was 1 over LC. So what I have is 2 over LC1 times LC. Okay, now let's acknowledge real quick. We said that C1 equals C2, and we said that they're both going to be equal to 1/2 of the total capacitance. So therefore, I can express C1 is equal to 2C. So let's plug that in over here. And now I've got 2 over 2LC times LC. That just equals 1. So A equals 1. That's sort of the first part of the first part of the partial fraction decomposition. Okay. So now let's go on to get the next one. And this way of evaluating and isolating terms, like I mentioned, it doesn't really work well for the spirogravitator. So let's manipulate this, and we'll say that f of s, I'm going to add up these two fractions. So I'm going to have a times s plus alpha squared plus beta squared plus ds plus e times s. And then that's all divided by my denominator, s times s plus alpha squared plus beta squared. And so I can see that if I multiply this entire denominator by my f of s equation, then that will remove all of my denominator on the left-hand side over here. And so then maybe I'll express this as, therefore, a times the denominator, s plus alpha squared plus beta squared, plus, here I'm going to have ds squared plus es. That's just going to be equal to 2 over 2LC. Sorry. 2 over LC1, which is equal to 1 over LC. I think I did that right. Yeah. Okay, so we've already mentioned that A is just 1, so let's just pen that in right here. So now what I have to work with is all of this stuff. And in this case, what we should do is try out different s's. Now remember, up here, we already tried s equals 0, which got us the A term. So now let's just try s equals -1 to start with. So what we're going to get is, yeah, how do I want to express this? We have -1 plus alpha squared. And so I'm going to break this term out, because that'll be -1 times -1 minus, so that's +1, minus 2 alpha, plus, and then we're going to have plus alpha squared plus beta squared. So I'll just write plus omega squared here. because yeah, alpha squared plus beta squared equals omega squared. Okay, so then I'll have plus D minus E. Because S is -1. So that gets us one equation. Let's try another one. S equals +1 and see what this gets us. Here I'm going to have +1 plus 2 alpha plus omega squared plus D plus E. And I'm going to call this equation 1 and 2. All right. Now, of course, you've seen this before, but if we do 1 plus 2, we add these equations together. I can see that my two alphas is going to cancel out, so I'll have 1 plus 2 omega squared plus 2D, and my e's will cancel out. Now remember, the right-hand side is just 1 over LC on both of these. So here I'm going to get that this is equal to 2 over LC when I added them together. So let's go ahead and solve. Now we'll solve for D. So 2 over omega squared is 2 over LC. Oh, and I should, when I added these together, 1 plus 1 is 2. And I see that 2 over omega squared is equal to 2 over LC, so I'll subtract that over and it will cancel. And lo and behold, I got that D is equal to -1. It's also, it's 2 over -2. Or sorry, really it's -2 over 2. Anyways, so that's how I can get D. You can find E using the same method. So instead we'll just say 1 minus 2. And what we get when I'll subtract those, and then I'll have -4 alpha. Then I have +0 plus 0D, so +0. And then 1 minus 2 would be -2E is equal to 0, because 1 over LC minus 1 over LC is 0. Okay, so therefore we get that. One sec, I think I missed something here. I mean, this all looks correct to me, but we'll see if it comes out with the correct value. Sometimes it doesn't. So we get that this is E is equal to +4 divided by -2 times alpha. So that's -2 times R over L. And here, oh geez, sometimes this writing surface is kind of a pain to use. So this is equal to -2 times R1 plus R2 over L. And I must have made a mistake because I think I'm off by a quick turn. So let me just pause this video real quick and check something. All right, so I found out that I didn't make an error. It's just that the way that this was factored in the solutions that I have, I'll just quickly show it to you. They did something brilliant where instead they just have the 1 over S LC plus 2 R2 S over L. So it's almost like what they left in their numerator for partial fractions was just all of V1. So they did not remove this R2 term like I did. However, we solved this correctly as per what's on the screen. So we can move on here because the problem's essentially finished. So now we have that V1 of S is equal to my partial fraction. So that's 1 over s plus, here I have negative s, that's the ds, plus e, which was negative 2r over L, divided by s plus alpha squared plus beta squared. So that handles the partial fractions. And then we also have to take into account the plus, this was R2 over, maybe I should express this as R1 plus R2. And let's make sure we're on the right track here with I of s being all of this. Maybe I'll just copy that to speed stuff along. So that's what that term was. And then we also have the minus 1/2 s. So that's minus 1/2 s. And I can see that these 1 over s terms will get removed. And I can also see that this 2 over L R2, so that will turn into negative s plus, here I'm going to have, one sec, if I do 2R2, give me a moment. I'm just going to write out what it is because this is quite a long derivation and I'm kind of running out of steam here. So this should turn into R2 minus R1 over L. So that's minus S over R2 minus R1 over L. Let me make that a bit more clear here. And then over S plus alpha squared plus beta squared. And then I want to also subtract off 1 over 2s because we added these constant terms together. So that's v1 of s. Equals this. And I'm going to leave this last part up to you. We can discuss it in lab if you have questions, of course. But it's your job to show that this v1 of s, for the most part, it follows, it's going to follow this cosine. That's the minus s term plus this stuff, the R2 minus R1 over L. That's actually a sine term minus some constant in the time domain. And the trick you have to use, I'm just going to make this note, for the cosine portion, you have to use that minus s over s plus alpha all squared. I have a typo right here. Plus beta squared. This is equal to negative s plus alpha minus alpha, all divided by my stuff. And this plus alpha minus alpha is how we can get it into this cosine form. So I'll leave that up to you. Please reach out on Canvas or email to ask these questions if you're still not getting that. So in the interest of time, I'm going to move forward with the MATLAB derivation. And let me quickly pause and unpause this. So just a moment. Okay, so we're back. This is the MATLAB section of the code. And I'm excited to show this to you because it's useful to watch how somebody goes about coding and you can learn their problem solving techniques. Now, what I really don't want you to do is to just skip to the end and copy my code. If you do that, you are completely defeating the purpose of this exercise. I don't want you to copy my code. I want you to learn how I'm problem solving. That's why I'm filming this video. So please follow along with me. but I'll show you how I go about thinking about this. So I'm reading the lab notebook for the first time. This was exactly how I did this. I see that part 5 right here, use MATLAB to plot the spirals that you expect on the oscilloscope by letting x equal v naught and y equal v1 and plotting y versus x. Okay, so I'm going to go into my MATLAB script, Control Alt Enter. We'll add new cells. The very last thing I'm doing, that's where I like to start my code, is the last step. I'm plotting x versus y, just like they asked me to. So v naught versus v1. So I can already see that if this code is going to work, I need a v naught term and I need a v1 term. Okay, well, I kind of know what those are already. I know up here, we discovered that v1 is this, so that's alpha dot times the exponential of, and sorry, I think I mistyped that. That should be control. That should be a dot times the exponential of negative alpha dot times t. So that exponential is also multiplied by a sine of omega dot times t. So I can already see there's all these new variables in here. So I'm going to need an a term. I'm going to need a t term. I'm going to need an alpha term. That should get me through that. Okay, now what about v1? v1 is of this form. Oh, and I realized that that's not omega, that should be a beta. So beta. We also need a beta term. And for consistency, I think I'll keep them all lowercase, just for style points. Okay, so I see that v1 also depends on these decaying sinusoids. So I'll just copy that twice. And I have to fill in the blanks. I know that my a will become a b here. This will be a cosine. That handles this stuff. And I should have a b right here. So instead of a beta, this should be a b. Now here I have a d term. I have negative alpha t sine beta t plus psi. So beta t plus psi plus c, my constant term. Okay, so now we go through the circuit parameters. They tell us that we have these constraints on our system, which really simplifies some stuff. So we already know that d equals 0. We know that, I think that's supposed to be a equals b, actually. Seems like there's a typo on this specific lab. So a equals b. And here I've labeled these as uppercase, and this should also be a capital B here and a capital B here. So now maybe down here I'll just write B equals, or sorry, capital B equals A. I will put that right here for style. That gets me through all my terms except for psi. Okay, psi is equal to 0 for now. Since we set d equal to 0, this part of the equation will never be computed. C is equal to my constant voltage of 0.5 volts. So all I need to fill in at this point are t equals alpha, or my alpha, and my beta term. So that's pretty easy. Now, t, I'm just going to try out a lin space. So this is a linear spaced array, and it starts at 0 seconds. It ends at 10 milliseconds. And let's put 1,000 data points in there. We'll see what that generates. Now for my alpha term, I forget what that was. I wonder if it's actually in the lab handout, but it should just be R over 2L, right? Yeah. So alpha is equal to, so it's R1 plus R2 dot over L. So R1 plus R2, I can already see I need new terms. R1 equals R2 equals. Let's just try 100 and 200 for now. See what that gets us. Let's try L equals 100 millihenries. They actually suggest we use that somewhere in this lab handout. Can't remember where. Yeah, L equals 100 millihenries. Oh, and here's my alpha and my beta term that I can start with. So they actually tell us that alpha is equal to 5 kiloradians. So that's, I'm gonna copy this. Alpha equals 5e to the 3, 5,000. So what does beta equal? Well, here I can see that beta equals 2 pi over t. So I'll pen that in. 2 dot times pi dot over the period. And what is the period equal to? Capital T is equal to 1 over 3 alpha. So 1 dot over 3 dot times alpha. So I think this will run. My A term, for now, I'll just set that to 1. That's not what it is. It depends on these values, actually. But I'll let you discover how to relate our time equations that we derived previously. How do you relate those A and B terms? It's all in the previous derivation. So I'll let you save that for your code. But at this point, I've put everything in here, I think, to get this to run. So let's give it a shot. And I'm just going to merge these cells so that all I have to do is click Control Enter to run everything. This is not quite what I'm expecting. And I wonder why it's shaped like this. It does look like a decaying oscillator, but what I'm expecting to see is a spiral. So must have made some mistakes in here. Another thing we can check real quick to help with the debugging, because that's what we're here to do, is watch debugging skills. Let's plot T versus V naught, and let's also plot T versus V1. And I'll just throw that in a separate cell to speed up the runtime. So what I'm expecting to see here is actually two decaying oscillators. And for some reason, my current IDE settings make it hard to see this bottom graph, but I can see that there's only one here. If I say A equals 1 and run this cell, I should be able to see this bottom graph. MATLAB's being kind of weird, but there's only one decaying oscillator here. So I can see, I think that's my V1 term. So if I say, let's plot V1 as green stars with a line, this will make it really obvious which one is the error. So I can see that actually my V1 term is what's at fault. So it's all of this stuff. Let's go through this and double check that everything's correctly put in here. So cosine of B times T, I wonder if this is a typo right here. I feel like instead of B times T, maybe that's supposed to be a beta. And like I said, all of this stuff doesn't even get touched because it's all multiplied by 0. So let's try. And what about my C term? That looks correct. Here we go. It says that V naught shouldn't be a decaying sinusoid. Maybe let's try that and see what we get. Okay. That must be a typo. That this should be a minus alpha right there for sure. Let's try this other thing of doing a beta. There we go. We're seeing a spiral. So now we're getting closer to what we expect. Let's rerun this bottom thing to see if we get two decaying sinusoids. We do. This is what we expect, right? One decaying oscillator offset by 0.5 volts because of this C term, and another decaying oscillator centered at 0 volts. Okay, so now I'll merge these two cells because that's part of the troubleshooting's done. What else is wrong with this? I can see my spiral is too chunky. It looks like there's all these lines. If I want to clean that up, I can just add more data points. So instead of 10,000, let's do 100,000. And MATLAB's incredibly fast at calculating. So Control Enter, and see that only took a few seconds. Now I've got this nice smooth spiral. This is looking really, really great. Okay, so we can start to play with this now. Let's see if we can do some interesting stuff. If I want to also, on the same plot, let's also plot negative V0 and V1. Sorry, negative V0 and negative V1. What does that get us? We see two overlapped plots, and they have some phase shift or some voltage shift here. If I set instead, I'm going to copy this line C, and I'm going to set C equals 0 and rerun it. I can see that they line up now right in the center, and that they're offset by 90 degrees, which you'll be able to actually derive in a subsequent portion of the lab. And I can also see that now my decaying oscillators are exactly overlapping. This is really cool. Looking at these two graphs, let me bring this graph into view by saying A equals and then I'm just gonna plot A transpose. Sorry, this dark themed editor comes with the price of being an experimental IDE, and so evidently the plotting still needs to be worked on here with whatever code they've written. But I can see my whole graph, and I see these two decaying sinusoids. I'm gonna just set that one as a green line real quick. They're exactly overlaying, and if I stare down the time axis of my of my plot on the bottom, I see this spiral shape, and that's really cool. Now, if I was somehow able to set this cosine and sine to be in phase, I could do that by subtracting pi over 2. I think this will work. I'm not entirely sure. Let's find out. I think that'll put them in phase. And yeah, we get a line now. That's interesting. That's not quite what I was expecting. I was expecting to see one spiral. Let's try a plus pi over 2 and see what happens. A negative slope. I'm not entirely sure what the reasoning behind that is. I was expecting to see the spirals line up perfectly, but nonetheless, this is kind of what we expect to get with our code, this sort of spiral. Make sure, of course, you should always add labels. So an X label, I'll let you all fill that in, and a Y label, and a title. Oops. So your plots don't necessarily need titles, but they definitely need X and Y labels to make everything super clear. And then as far as the rest of the code goes, you just need to figure out what your A and B terms are, because they're not necessarily one. And you can also, you can play with this a bit. Like, what if I shift the B term by 50%? What will I get? And you can see, maybe it's not apparent, but I believe that there's some stretching that would occur if I do that. Or let's set it to 10. Let's see what happens. Yeah, it's not obvious, but now the y-axis is 10 times bigger, and so this has squished it actually. I think no, stretched one way. There's some compression along one of the axes, but anyways, So that's what I have for today's video. I'm sorry it was so long, but this is a really long derivation, and I hope this MATLAB code was useful for you to see. I'm going to stop the recording for now. Again, let me know if you have any questions. You can always email me. Have a nice day.